but I really just want to give you a brief introduction to some of the different infrastructure that is used in the development of geospatial reference systems. So very long baseline interferometry. Quick show of hands. Who's actually heard of this term before? Good. Chris has got his hand up. Good. That's good. That's all right. That's all right. That's a good start. Satellite laser ranging. Yeah, it's good. GNSS. There should be a lot for that one. Good. 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 All right. You're all in the right room. Now, Doris, this will be a tricky one. Okay. Oh, wow. All right. I'm impressed. Okay. There will be a test, so I'll make sure if any of you are lying to me. All right. So who's heard of the ICRF? ICRF. Yeah. Okay. Now, the trick with this one is that you think about the ICRF, the International Celestial Reference Frame, is really the reference network that we're using to then define the International Terrestrial Reference Frame. You need to have a link between the Earth-based frame and the space-based frame. And the Celestial Reference Frame refers to, can you see up the top there, it says quasars. Quasars are the source points for the International Celestial Reference Frame, and they're big gas jets coming out of black holes. How cool is that? That's pretty cool, right? If you want to explain that to a minister, that's at least going to get their attention. You're talking about something that's pretty cool. So based on the waves that are coming from those, we use them as like point sources, and we assume that they're not moving because they're so far away, you can almost consider them static. So if you picture yourself, if you think about the Earth as a giant basketball in space that's spinning around, and you're sitting on that basketball, apart from being very dizzy, imagine trying to get yourself in a frame of reference. You need point sources where you can consider them to be part of your frame of reference. And that's kind of what the quasars are. They're these points in space that we can use as a fixed frame of reference. That's what the celestial reference frame is. And a lot of your satellites and all the different techniques you use, they're ultimately working within this celestial reference frame. So the critical part for us is coming up with a way to transform between a celestial reference frame and an Earth-based terrestrial reference frame. And that's what this one is. So this is where we assume that the center of the mass of the Earth is the center of our reference frame. And then we define the X, Y, and Z, as we showed before with our transformation parameters. And then we have the scale, how big is the Earth, and then how quickly is it rotating. So we come up with these parameters and define the International Terrestrial Reference Frame within that ICRF. There's some great links down there on the bottom as well that takes you through to more information. You can read about this later on. Then there's a range of different other gravimetric geodetic techniques like gravimetry. On the left, that looks like an FG5. Jack, what do you reckon? Yeah. That's helping us measure the absolute gravity of the Earth at different points. And then you can have relative gravimeters as well that link back to these absolute points. And you're using that for things like geoid model development. You then got leveling, altimetry, tide gauges. All of these different geodetic techniques need to come together if you're going to make good decisions. There's a range of sites where you can see here the stars represent VLBI stations. The green diamonds are the SLR, GNSS, and DORIS. You can see that compared to the other techniques, GNSS is pretty widespread. There's a really good spread, really good geometric coverage around the Earth, similar to DORIS. Like DORIS is a network that's been designed, and it's primarily under the control of the French government. So they manage and control that very well. And therefore, they've got great distribution around the world. The other SLR, VLBI, they're a little more ad hoc. And it's very much driven by, in the past, where could we steal time away from the astronomers? It's the astronomers that have traditionally been really good at getting the funding to set up satellite, to set up their antennas and get observations done. And we've had to try and take advantage of where those antennas already are. There's also an over-reliance on the academic sector. So those antennas are sometimes set up by the universities, and we're trying to access time on those for geodesy. So we haven't set up that SLR or VLBI network in locations where we actually think we need them the most. It's been much more ad hoc on where we can take advantage of what already exists. So VLBI, we measure the time difference. You can see quasars there on the top left. So the quasars send out signals, and based on the difference in time that it takes to reach different antennas, you can measure a couple of things. Firstly, you can measure the difference in distance, the baseline between two observatories on the ground. And then using a collection of this data, you can also measure the spin rate of the Earth, which changes slightly over time. This is critical for things like not just for positioning and station locations of the stations, but VLBI is also the only technique that can measure the spin rate of the Earth. And that is a critical parameter for that wobble that I talked about before. The Earth orientation parameters that we develop, they're unique. That timing one is uniquely defined by VLBI. That's what makes VLBI so critical for our day-to-day geodetic analysis. I won't harp on any of the maps. We've talked about that before. This one is around being able to measure those source functions. And what do you see? Is those defining sources, or the sources that we use in the International Celestial Reference Frame. You can see that we don't have as many in the Southern Hemisphere. That's what we're trying to highlight here, because we have less of the infrastructure in the Southern Hemisphere to do that analysis. So what that can do, and they've queried, is whether or not this can cause a bias in the determination of your reference frame, because you've got less defining sources in the Southern Hemisphere. So we really need a good geographic distribution of those stations around the world. Here's what they look like. There's all different shapes and sizes. There's a 20-meter dish on the far left-hand side from Wetzel in Germany. These are all actually German ones, including the one at La Plata, which is in Argentina. It's co-run between Argentina and the German government. But you can see we're taking advantage of things that already exist. There's not a standard network that we use to do this type of analysis. And you need the big dishes to define the sources in the ICRF. And then you need some of the faster, smaller dishes to do some of the observations for the day-to-day activities. Satellite laser ranging. It's exactly what it says on the tin. You fire lasers at satellites to range and get the distance between them. So this helps us understand the orbits of the satellites. It also helps us define the reference frame. So using some of the satellites that have little corner cube reflectors on them, or some of them look like giant golf balls with dimples in them, they're really good at reflecting accurately back to the Earth. And then they help us tell us the center of the mass of the Earth and how that's moving over time. And you can measure that at the centimeter level using a range of different techniques. And there's the locations of those around the world. And here's what they look like. Some of them are covered, most of them are covered with domes. And then the laser can point out through the dome. They have an opening that can move around. GNSS, I think we all understand quite well. Whole range of different techniques that we use: GPS, GLONASS, Galileo, regional systems, QZSS, and also the safety of life systems as well that are interlinked with GNSS, like EGNOS and WAS. QZSS does QZSS have one of those signals as well, a safety of life system? Yeah, as well. And then SouthPan with Australia and New Zealand. Much better spread around the world. Good geographic distribution. I don't think there's any threat of that network failing. That's one of the strong points that we have. And then Doris, which you all know about from the sound of it. I think about it like GPS in reverse, where you have the active part on the ground and you've got the recorder in space. And this it helps to remove some of the biases. This is what I was talking about. They're all complementary techniques. So you combine Doris, VLBI, SLR, GNSS. You've got a whole range of different techniques that can measure different information and complementary information that together help us define the movement of the Earth over time. And gravity, we need the physical geodesy. We have the absolute gravimeters, and we have relative gravimeters, as I mentioned. And then you can have different types of measurements. You can have terrestrial, airborne, satellite. You can have shipborne as well, which is really useful for the marine space. And this is really to help us develop an understanding of the physical shape of the Earth, and also help us with center of mass observations and monitoring some of the dynamics, which is particularly important for some of the natural hazard cases that we mentioned. Here's the example of where it's all gets brought together. So this is a great picture from Wetzel where they've got all these different techniques. So this would be called a core site. Sometimes I like to call it when I'm talking to a politician, I'll call it a super site, because they can understand that it's got everything together. It's got the radio telescopes, it's got gravimetry, Doris, VLBI, SLR, GNSS. They've got timing there, and they also have a ring laser, which is another way of measuring the spin rate of the Earth, using another laser-based technology, but it's a localized piece of technology that they also, I found out recently, have in New Zealand. And there's been a great collaboration between the German government and New Zealand government on works on ring lasers. So having these together, as I said, they're complementary techniques. And the beauty of having them together is that then you can then integrate them. So you do a land-based survey using something like a total station to then link these together using terrestrial observations. These are called local tie studies, where you observe the difference between the GNSS, the SLR, the VLBI. And here's a picture of where they've done that at Wetzel. And you can see all these different lines connecting them. They've been measured using a total station on the ground. So when then you're doing the ITRF determination and you're bringing together SLR observations, VLBI observations, GNSS, Doris, you can bring it all together and link them with this local tie effect. So that's why these local ties are so critical in the determination of reference frames. And then there's timing and frequency as well. They're probably used less by some of the traditional mapping agencies, and you may have an independent agency that's working on timing and frequency standards within your countries. My advice, though, is get to know these people, because having an understanding of how vulnerable these timing and frequency stations are, this is really underpinning the critical infrastructure systems in your country. So if you don't know who these people are that are running timing and frequency, if they're not in your agency, go and find them. Work out who's in charge of the timing standard in my country. Make them your new best friend. In Australia, I call him the Time Lord, like Doctor Who. They're very important people to know. So go and find them, because if their system fails, critical infrastructure systems, internet, things like that can start to fail in your country. And there's a strong link there with Geodesy, because we're both using similar information. Go and meet them. Here's one of the weaknesses that we highlighted. Where do we have these co-located? Ideally, you'd want probably 3 or 4 of these green or red dots on every continent. And as I showed you before, we just don't have that. We have it in Europe, but nowhere else. And to me, that's a real reliability gap. You know, that system, that supply chain's not robust enough. And it's only going to take a couple of things to stop or break, particularly when some of these ground infrastructure systems, they were installed as mobile systems over 50 years ago, and they stuck together with sticky tape and chewing gum sometimes. They're not reliable enough for the future, and people don't realize it. So if you have one of these in your country and you haven't been to visit them, go and visit them. See what they're doing, see what they need help with. And then here's just a map more so for you to come back. I don't want to get into detail here, but you'll touch on one of the things that I mentioned around timing and the criticality of things like VLBI. You can see that length of day observation. That's a really critical parameter for the determination of Earth orientation parameters, understanding the spin rate of the Earth, and it's uniquely done by VLBI. So you need to be able to measure that in order to have satellites working accurately and reliably. That's the story that you want to tell when you're talking about trying to put VLBI in your country. If you don't have good VLBI, eventually satellites will degrade and fail, because we won't have a very good understanding of the Earth's spin rate. And if you're off by, a few microseconds, it can cause kilometers off in terms of GPS positioning. So that's a substantial impact that you need to be aware of. Some further reading there around the ITRF and ICRF. And there's also, in particular, the second page that's going to link you through to geodetic techniques and services as covered by GGOS, the Global Geodetic Observing System. They've got a great website that talks about all these different techniques and the impacts of these techniques around the world. So I'd encourage you to go and have a look at those if you're trying to get a bit more background information on the different geodetic infrastructure that we've covered here. So I'll stop there, and I'm happy to take a couple of questions before we go for lunch. Thanks, everybody.
Nick. I was wondering if you might be able to comment on the kind of interdependency of these techniques, like particularly VLBI and precise timing. Yeah.
Yeah, sure. So I'll maybe use it as I'll use an example of how I've been trying to describe it to politicians in Europe recently. And that is, if we go back to actually, I'll use the co-location one. This one here. So if you have a look, you'd notice that those, as I mentioned, the red and the green, particularly in the Southern Hemisphere, there's not many of them. And the story that I've been explaining to politicians in Europe is that out of all of those, the only one that they really have any control over is the La Plata one, where it's co-run with the German government, but it's also co-run by the Argentinian government. Now, the vast majority, not all, but the vast majority of all the other ones that are in the Southern Hemisphere are managed by or co-operated by the United States government. So if the United States government decided, I don't want to share that information with you anymore, would you be able to run your satellite systems that are run by ESA? In the short term, sure. But in the long term, would they degrade? Yes, because you don't have the information coming from satellite laser ranging and very long baseline interferometry. In particular, my feeling is around the VLBI, that VLBI is that uniquely is determining the spin rate of the Earth. And therefore, it's uniquely determining one of the very important Earth orientation parameters. And it has been shown that you can estimate what the changes are in the length of day without using VLBI, but it's, as to use an analogy of gravity, you'll get a drift. So in gravity, how you're using different clocks to accommodate for short-term and long-term drifts. You do the same thing with VLBI, and VLBI is our way of keeping us close to what the true baseline would be and avoiding that drift away. So eventually, every now and then, you need VLBI to remove that drift and bring you back. So if you don't have VLBI, that's where you're going to struggle. And then on the satellite laser ranging, that's doing something different. That's helping you understand the center of mass of the Earth. So VLBI is more on that scale parameter. SLR is helping you with the center of mass of the Earth parameter, and also helping you monitor the orbits of your satellites and how they change over time. So stations like Yarragadee and Stromlo in Australia are very key because they're really the only two in that. They're the only two SLR systems in that region. So they are providing really critical input for center of mass determination over time. Because if you've got nothing from that region, you will see a bias in center of mass determination. We've demonstrated that. And also you get a vast reduction in how well you're tracking things like GNSS satellites and the orbits of those satellites. So the accuracy of that information from those satellites would degrade over time without them. Any other questions, or are you all too hungry? Richard, yeah.
Did you want to explain the difference between the ITRS and the ITRF? I mean, it's a subtle distinction, but it might be worth mentioning.
Yeah, systems and frames. So I remember when I first started studying geodesy, this really confused me. And so I'll tell you what I think it is, and then I'm happy to be told that I'm wrong. A system is more like it's a collection of things and how they're brought together. But it's not a realization. So a frame is the realization of that system. So to give you an example, you can talk about having a VLBI network and a satellite laser ranging network and a GNSS network. They're all part of our positioning system that we use around the world. So that would be part of the International Terrestrial Reference System. But when you talk about a frame, you're saying we are realizing that system. We're going to take that system and we're going to make it practical. We're going to make it realistic. And so it's defining what VLBI stations, what SLR stations, what GNSS stations, and what assumptions did I make when I took that system and I've converted it into something that I'm going to use and has a practical, concrete realization. That's the way that I think about the distinction between a system and a frame. And it's almost like you might talk about a system and your datum. When you define your datum legally, you will have to define what are the reference points in your country and what are the coordinates of those reference points in your country. So you're taking this ethereal definition of what a datum is or a coordinate reference system is, but you're fixing it to these defined points in your country that have this value and it has this uncertainty. So it's really that practical realization is what I see as the distinction between a system and a frame. But I'm happy to hear other people's answers because that's the best that I've got, and I know it's not perfect.
And how would you like to distinguish between the regional frames like APREF? So now sometimes there's like a bit of confusion. Like ITRS is a definition. ITRF, it's realization, global realization then. Then APREF, it's still a reference frame, but where's its definition? Because then people would like to distinguish between frame and the datum. Right. So this is some kind of maybe definition differences that we are facing. Right.
Yeah, I think these are great questions, and they're things that I've struggled with a lot. And I don't see a big distinction between a frame and a datum. Datum is often the use that you'll use for your country, but how different is that to a frame? It's not really any different. I consider them both to be practical realizations. I think the definition around APREF, and we'll have a presentation on that. Again, it's a practical implementation, and in the way that the Central Bureau within Geoscience Australia realize it and create that frame is that every week they publish a new coordinate set. So that's the coordinate set aligned with this regional reference frame. So it can be complex, but I think we have, particularly with the Australian Geospatial Reference System Compendium, for the Asia Pacific region, we've tried to provide clearer definitions of what these things are and how they've been implemented. And I think that helps tell a bit of the story. But yeah, we as geodesists are our own worst enemies when it comes to terminology. When I started working with Jack on gravity stuff, I realized it's the same with physical geodesy. Quasi-geoid, geoid, telluride. I still wake up in hot sweats thinking about that stuff. It drives me crazy trying to understand the terminology. So I think coming back to what I said before, I think we've got to get better at maybe focusing less on single words and coining terms, but writing things out in more detail. I think that's the way that we get through to people. So I hope that answers your question, but keep asking those kinds of questions because I think they're critical to help people realize what we're actually talking about and is it the same thing as that? Yeah.
What question or comment on the local survey? You showed us a slide on the role of the local Thai surveyor on the combination of the different technicals to construct the ITRF. And as we know that the local Thai most of the local trials are conducted only once or up to twice in a long history. And due to some geophysical reasons or some mankind, for example, exchange of the antenna or receiver of the GNSS. So the local data may be changed, but we have only one. So as I always consider that question that is it possible to make or repeat of the local tile? This one tile, and another thing is that to more local in more stations. As you know, the local distribution is also not globally, only some regionally or something like that. So this is my one comment. Okay.
Yeah, it's a great point, and I agree with you. I think the recommendation is that they should be done about every 18 months or 2 years, but there's not a lot of expertise around that can do these kind of surveys. And even if you can do the survey, there's not a lot of expertise of people who can do the analysis to bring all these different techniques together, because a lot of them are they're invariant reference points, which means you can't actually measure to the center of an SLR system or to the center of a VLBI system. You're actually taking a collection of measurements from all around it, and you're trying to infer where the reference point is based on all the measurements. So you need specialist skills, specialist techniques and analysis to try and do this work. So we don't have enough people who can do it. And that VETSL survey probably takes between one and a half and 2 weeks. They take a very long time to do such high precision surveys. So you've hit on a really important point, that they're not done often enough, and we don't have a lot of people who can do it. To try and deal with some of these biases, you may have heard of the Genesis mission, which is being launched by ESA. And this is about, it's a combination of the techniques, but in space. So it's a space-based combination rather than an Earth-based local tie. So that's trying to help deal with some of the biases of the complementary techniques and solve that by co-locating them in space. And that's due to be launched in the next few years. So we're hoping that's going to help. But in the meantime, we're still reliant on people having the time to do this critical work on the ground, and hopefully having the analysis capability to do all the to do all the analysis work as well, which is very difficult to do. Have you got any experience in doing that yourself?
Yeah, thank you. Thank you. May I have another issue or same as this one? That, as you know, the GGCE goals is for to 1 millimeter precision and 0.1 millimeter per year for the velocity. And you also say that the current ATRF is only at its level of 5 millimeter. So that means the historic local survey data may be enough for the current ATRF. But if for the GGCE goal for 1 millimeter, I think most of the old local high data is not enough. So that means we need to make or repeat all the local survey. Okay, thank you.
Yeah, you're exactly right. It was one of the very strong business cases that ESA made for the development of this mission, was to help drive the accuracy of the reference frame down to that goal of 1 millimeter. It's unlikely that you'll be able to achieve that using the ground-based local tie technique. So this is where we're hoping the Genesis mission will help improve the quality of the reference frame in the future. So it's an excellent point. Due to the geophysical reasons on the ground, it's very hard to get that level of accuracy. It's going to be almost impossible to get to that 1 millimeter level without some sort of co-location in space, I think. Yeah, good points. Thank you. Yes, thank you.
Regarding the future stations of, for example, for VLBI and IRS, what is the consideration that the station will put at that location? Is there any geometrical consideration that if we put the station at the location, we will be improve the quality of the product? And how the process to convince the host of the country to accept that the station will put on their country?
Yeah, there's been some wonderful work done by people within the IAG, the International Association of Geodesy, to do simulations to work out if we put a station here, what would be the impact on the reference frame or on Earth orientation parameter development to bring down the uncertainties associated with them. So there has been a lot of work that's been done from a scientific point of view. The bit that we've lacked is the translation of that science into policy. And the main reason for that is because there is nowhere to take that information at an international level to seek funding. We don't have that international policy group of decision makers who can say, we think that we need more infrastructure here, it's going to improve the supply chain. So this comes back to a governance issue. The IAG can come up with great recommendations, but they're like us. They're a collection of mostly scientists from their countries. There's nowhere to go to get funding to try and implement that. And it's very difficult for a country to go on its own to say, let's say you went to your minister in Indonesia and said, I want to put in a VLBI site because it's going to improve the reference frame by 1 millimeter and we're going to get more accurate Earth orientation parameters. Your minister is just going to say, why am I fixing this problem for people on the other side of the world? You're essentially putting infrastructure in so that other people will get the benefit. Why aren't they paying for it? So this is where the need for an intergovernmental organisation comes in, so that member state contributions are going to solve global problems and decisions are getting made by an intergovernmental council to say that's where the funding for infrastructure needs to go because it delivers on these needs of us globally. Until we have that international governmental organisation, I think it's going to be extremely hard for people to develop the funding proposals to sustain the infrastructure requirements that we have around the world. And we'll be stuck using these sort of ad hoc options that we have at the moment for SLR and VLBI.